Hello, welcome back to my channel, The Math Explorer. In this video, I will discuss with you what is Galois group, what is Galois extension, how to identify Galois extensions, and how to find out Galois group of a given polynomial. So let me start. First of all, we will start with the definition of Galois extension. Galois extension. So suppose you are provided with an extension k over f, which is a finite extension. What do I mean by finite extension? Is extension which is generated by finite number of elements. Okay, so for example, suppose I'm considering q root 2 as an extension of q. Okay, then root 2 satisfies polynomial x square minus 2. Okay, so the basis of q root 2 over q will be powers of root 2 until 1. So root 2 raised to 0, root 2 raised to 1. Okay, so basis is nothing but 1 comma root 2, and we can easily identify that this particular extension has a finite basis over q, as it is generated by two elements over q. So that's why this extension is finite extension, right? But if you'll talk about any other extension than this, then we can provide example that real number is an extension of rational number. But it is quite obvious that real numbers cannot be generated by finite number of real numbers over rational numbers. So this particular extension cannot have a finite basis, so it is an infinite extension. Okay, no all real numbers can be generated by a finite number of real numbers over rational numbers. Okay, so that's why this extension is infinite extension. So first of all, to identify whether a given extension is Galois extension or not, it must be a finite extension. Okay, so let me start with a finite extension. So let k over f be a finite extension. Okay, now the question is, under what condition we can say that it is an Galois extension. So to identify that, we have one result with us. Result reads as, suppose E is a splitting field of a polynomial f of x belongs to fx, then set of all automorphisms of E over f, the number of automorphisms is less equal degree of extension of E over f, right? And equality holds if f of x is separable over f. Okay, this particular theorem has explained in the previous video, so I urge to visit that video and watch out how can we prove this particular theorem. So the general condition is that set of all automorphisms of E over F has cardinality less than or equal to degree of given extension. So an equality holds if and only if f of x is separable over f. Okay, so now we'll continue with the definition here. So k over f be a finite extension, then k is said to be Galois extension of f, or k is said to be Galois over f if cardinality of automorphisms of k over f is exactly equal to degree of extension of k over f. Basically, this remains less than or equal to, but if this is equal, that number of automorphisms of k over f is exactly equal to degree of extension. Under that condition, we can say that k is Galois extension of f. And if this is so, this set of all automorphisms, so let me just write it as a note. If k is Galois over F, then corresponding automorphism group, which is out of K over F, then corresponding automorphism group out of K over F is regarded as, or we may say symbolized as, GAL K over F, Galois group of K over F. Okay, so now we will try to utilize the result that we have already seen, and we'll try to accomplish one corollary here. This particular theorem says that equality holds if f of x is separable over f. That means if you are provided with a separable polynomial, means a polynomial with distinct roots, where each and every root of that polynomial is simple, means it is not repeated more than one time. Okay, so if such a polynomial is given to you, that is going to be separable polynomial, and its splitting field, suppose E, is gonna be Galois over F, because in that case equality holds. In that case, number of automorphisms of E over F is exactly equal to degree of extension of E over F. So we can write one simple corollary here. So let me write that corollary now. If K, which is extension of F, is found to be, suppose, a splitting field. If K is splitting field as per the result that I have shown you just now of a separable polynomial, of a separable polynomial over F, say f of x, then K over F is Galois extension. Now let us support this corollary with an example. So I will take one example. Let f of x equal to, say, x cube minus 1 belongs to qx. Right? Now we will find out the roots of this polynomial. So roots will be simply cube roots of unity. So 1 comma omega square are roots of f of x, right? Where omega is a cube root of unity, right? So to find out splitting field of this polynomial, we only have to attach these roots to base field q. Thus, it's simple that we have to attach omega, because as soon as we attach omega, we'll find that omega square is also in that splitting field. So thus, q omega is a splitting field of x cube minus 1 over q. Further, you'll find that this particular polynomial is separable because each of the root of polynomial is distinct, 1 omega square, none of the root is repeated. So this is separable polynomial, right? So I can write that clearly, f of x is separable polynomial because it does not have a multiple root. Okay, so we can find that q omega, so let me just highlight it. So q omega is splitting field, right, of separable polynomial. So if you use previous result, equality holds if f of x is separable over f, if you use that result, we can simply write here that number of automorphisms of q omega over q will be equal to degree of extension of q omega over q, okay, which is actually 2. So this will happen because degree of extension is 2 because omega is a primitive root of unity, so it is root of x square plus x plus 1, so it will have two roots, omega and omega square, so omega can map to omega or omega can map to omega square. Basically x cube minus 1, the fact that I've just said is this: x cube minus 1 is nothing but x minus 1 into x square plus x plus 1, okay, and the roots of x cube minus 1 are 1 omega omega square, where 1 is root of this factor, right? So obvious thing is that omega and omega square are roots of this particular factor, and this is gonna be a cyclotomic polynomial which is irreducible over q. So this is minimal polynomial of omega, and that's why omega can have two images, either omega or omega square. So that's why there will be two automorphisms, okay, and degree of extension will be 2, okay. So that's how we can establish the fact that q omega is a splitting field of separable polynomial. That's why by previous result, number of automorphisms of q omega over q is exactly equal to degree of extension of q omega over q, which is 2, right? So that is the reason q omega is a Galois extension of q. So hence q omega is Galois extension of q. So diagrammatically we can write it like this: q omega, that is extension of q, right? Omega satisfies polynomial x square plus x plus 1 over q, which is a cyclotomic polynomial, so irreducible. That's why basis will be powers of omega until 1. So omega raised to 0 is 1, then omega raised to 1 is omega, so this is basis of q omega over q. Thus degree of extension is 2 because it is generated by basis of two elements over q. So degree of extension is 2. And on the other hand, if you are asking about automorphisms, then any automorphism of q omega can be obtained by image of omega, because omega is an element attached to q. So omega can map to omega or omega can map to omega square. So omega can map to omega or omega can map to omega square, right? So based on this fact, I can write two distinct automorphisms of q omega over q. First one is 1 maps to 1 and basis element omega maps to omega, which is identity automorphism. Okay, so this is first one, and second automorphism can be identified as 1 maps to 1, right? And omega maps to omega square. So these are two automorphisms. So number of automorphisms is 2, degree of extension is 2, both are equal. So that's why q omega is Galois extension of q. So in this way we can support our corollary. Now after this, let's go to another definition, and then we'll go for some additional examples based on Galois extension. So let me write definition. If f of x is a separable polynomial, if f of x is a separable polynomial over f, then the Galois group of f of x over f is the Galois group, it's the Galois group of the splitting field of f of x over f. Splitting field of f of x over f. Okay, so we can write as example the previous example that we considered. For example, Galois group of q omega over q will be equal to identity map, say E, and another map, say sigma, where Sigma is defined like this, where 1 maps to 1 and omega maps to omega square, right? So that is sigma. E means 1 maps to 1 and omega maps to omega. So that's why this is Galois group of q omega over q, which is actually nothing but the Galois group of splitting field of that polynomial over q. That is just an example. Okay, so this is definition of Galois group of polynomial. Now I will move to some examples to elaborate the idea of Galois extension in more detail. Okay, so firstly I will consider a very familiar example that we are considering since previous videos, that is q root 2 is Galois extension of q. Q root 2 is Galois extension of q. Why this is so? So reason is quite simple. First of all, we can identify that root 2 satisfies the polynomial x square minus 2. It has two distinct roots, root 2 and minus root 2. Okay, so basis of q root 2, clearly we can write here the minimal polynomial, or I will write the minimal polynomial, the minimal polynomial of root 2 over q is x square minus 2, right? So basis of q root 2 over q is 1 and root 2. Root 2 raised to 0 is 1, root 2 raised to 1 is root 2, because degree of minimal polynomial is 2, so basis will be powers until 1. Okay, so this is basis. So this clearly implies degree of extension of q root 2 over q is 2, right? So this degree of extension is equal to 2. Let me write this first. Now let's find automorphism group. Now the roots of minimal polynomial of root 2 over q, that is x square minus 2, are root 2 and minus root 2, right? So we have, and both of these roots are in q root 2. Both of these elements are in extension. So root 2 can either map to root 2 or root 2 can either map to minus root 2. Okay, thus root 2 can map to root 2 or root 2 can map to minus root 2. So based on this fact, we have two different automorphisms. We can write identity automorphism. Identity automorphism, in that case, basis element 1 maps to 1 and attached element root 2 of q root 2 maps to root 2 itself. So this is identity automorphism. And another automorphism, say sigma, can be expressed like this, where 1 maps to 1, because each of these automorphism must fix q, right? Automorphisms of q root 2 over q, so q must be fixed. That's why 1 must map to 1, and the attached element root 2 maps to minus root 2. So this implies automorphisms of q root 2 over q, that's it, equal to e and sigma, where e and sigma are as depicted here. And so cardinality of automorphism group is equal to 2. So I will call this as second statement. So if you combine first and second statement, you can easily tell that hence cardinality of automorphisms of q root 2 over q is exactly equal to degree of extension of q root 2 over q, and that's why so q root 2 is Galois extension of q. Galois extension of q. Now we will see one more example, which is not a Galois extension. So let me write a second example. Q cube root of 2 is not Galois extension of Q. Now why this is so? Explanation is quite simple. See, first of all, you have element cube root 2. Okay, the minimal polynomial of cube root 2 is going to be x cube minus 2. The minimal polynomial of cube root 2 over q is x cube minus 2, right? It's quite simple, because if we take x equal to 2 raised to 1 upon 3, and if you take cube on both sides, then x cube equal to 2. So that is the reason x cube minus 2 equal to 0. So this is a minimal polynomial of cube root 2 over q. Fine. Thus basis of cube root 2 sorry over q is powers of cube root 2 until 2. So 2 raised to 1 upon 3 means cube root 2 raised to 0. Then 2 raised to 1 upon 3 raised to 1, and 2 raised to 1 upon 3, because cube root 2 is attached elements, raised to 2, because minimal polynomial is of degree 3, so we have to go until power 2. So that is equal to 1, 2 raised to 1 upon 3, and 2 raised to 2 upon 3. So this is the basis of q cube root of 2 over q. So degree of extension of q cube root of 2 over q will be 3. So let me write this statement as 1. Now let's try to identify the automorphisms. Okay. Now we will find out the roots of x cube minus 2. The roots of x cube minus 2 are 2 raised to 1 upon 3, then 2 raised to 1 upon 3 omega, and 2 raised to 1 upon 3 omega square. Okay, where omega is a cube root of unity, where omega is cube root of unity, right? Now I want to identify automorphisms. So 2 raised to 1 upon 3 is attached element, right? And we have to just find out an image of 2 raised to 1 upon 3. Okay, the fact is that q cube root of 2 is equal to, because its basis over q is 1 2 raised to 1 upon 3 2 raised to 2 upon 3, so it can be written as a plus b into 2 raised to 1 upon 3 plus c into 2 raised to 2 upon 3, means 2 raised to 1 upon 3 square, where abc belongs to q. So to define any map on q cube root of 2, we have to just identify what is the image of 2 raised to 1 upon 3. Because if you identify the image of 2 raised to 1 upon 3, we can identify the image of all these elements in q cube root of 2. Now 2 raised to 1 upon 3 have minimal polynomial x cube minus 2, and these are roots of this minimal polynomial, but not all these roots are in q cube root of 2, because q cube root of 2 is gonna be a subfield of real numbers, right? And these omega and omega square are complex numbers. So that's why these two roots, 2 raised to 1 upon 3 and 2 raised to 1 upon 3 omega square, are not in q cube root of 2, because they are complex numbers. So there is only one root 2 raised to 1 upon 3 which is present in the extension. So 2 raised to 1 upon 3 can only map to 2 raised to 1 upon 3. Okay, because these two roots, even though they are roots of minimal polynomial, they are not present in extension. They are complex numbers. So that's why 2 raised to 1 upon 3 can only map to 2 raised to 1 upon 3, because we are defining automorphism of this field, right? So image should again go to this field, right? So basically the point that I want to make clear here is this. So if I'm defining a map from q cube root of 2 to q cube root of 2 self isomorphism, that is automorphism, it means image should be again in q cube root of 2. And if I take these two elements as images, they are not part of q cube root of 2, so we cannot take those as images. So only possible image of 2 raised to 1 upon 3 is 2 raised to 1 upon 3. And that's why only automorphism that we can find here is identity automorphism. Okay, so we can write that fact here, since 2 raised to 1 upon 3 omega, 2 raised to 1 upon 3 omega square does not belongs to q 2 raised to 1 upon 3 or q cube root of 2, comma, only possible image of 2 raised to 1 upon 3 is 2 raised to 1 upon 3. So only automorphism, identity automorphism, okay, where all the elements map to their own elements. So 1 maps to 1, 2 raised to 1 upon 3 maps to 2 raised to 1 upon 3, and 2 raised to 2 upon 3 maps to 2 raised to 2 upon 3. Okay, thus we can conclude here that automorphisms of cube root of 2 over q is equal to only e, where what is e? E means 1 maps to 1, and 2 raised to 1 upon 3 maps to 2 raised to 1 upon 3. That's it. So cardinality of automorphism group of cube root of 2 over q is 1. Let me write this as second statement. So you can easily combine first and second statement, and you can identify that the numbers are not equal. So clearly cardinality of automorphism group of q cube root of 2 over q is not equal to degree of extension of q cube root of 2 over q. Hence q cube root of 2 is not Galois extension of q. Fine. So here we stop. In the next part of this lecture, we will identify the following facts. We will try to identify and answer the questions whether Galois extension of Galois extension is Galois, whether Galois extension of Galois extension is Galois, so we will answer this question in the next lecture. Then we will try to whether q root 2 comma root 3 is Galois extension of q, and what is Galois group of x cube minus 2 over q. Right, and we will also talk about the fixed fields of subfields of automorphism groups in these cases. So stay tuned for these all answers. Thank you.